this seminar section on tactile perception and robotics. Today we are honored to host here three leading scientists, Dr. Alessandro Albini from University of Oxford and Dr. Elisaveta Konstantinova from Ocado Technology and Professor Giorgio Cannata from University of Genova. The first talk will be given by Ocado Technology. The talk will be about innovation and research projects on Ocado Technology. Dr. Elisaveta Konstantinova is a senior researcher and team leader at Ocado Technology, holds a PhD degree in robotics from King's College London. She has a background in academic research focused on medical robotics, tactile perception, intelligent grasping, and soft robotics. At Ocado Technology, she leads external research projects and collaboration aimed at long-term innovation. Currently, she serves as a principal investigator for Ocado Group on Horizon Europe projects Soft Enable, IntelliMan, and Sestosenso, which focus on intelligent manipulation of complex grocery items. So, please, Elisaveta, the stage now is yours.
Thank you very much. I'll give a talk about what Ocado Technology does and what research projects we are working on. Just maybe some notes. So for me, it's a comeback a little bit. So I got my bachelor's degree from Riga Technical University around 15 years ago. So for me, it's a nice time to give a talk here. What Ocado Technology does? So Ocado Technology develops solutions for online grocery distribution. So we are a technology company that is providing end-to-end warehousing, storage, and logistics solutions for supermarkets. So we have started with create our own supermarket. So in UK, there is a shop, Ocado, where people can order groceries from. And all the shop is online only, so there are no physical stores. And modern warehouses, which I will tell you about in a little bit. At Ocado Technology, we are more than around 5,000 people working in different domains: software engineering, artificial intelligence, robotics, and data science. And so a lot of smart people working on a lot of interesting projects. Okay, and the business model of Ocado Technology and of Ocado Group is to sell these warehouse solutions to different supermarkets around the world. So the biggest clients are maybe in North America. We have Sobeys, Kroger, Coles supermarket in Australia. We recently opened supermarkets in Japan and working with Korean partners. So there is a big spectrum and a big challenge for us to create those solutions. So just one more time, just to visualize how Ocado is organized. So the conventional way, there are delivery vans that bring goods to the warehouse, and then from the warehouse everything goes to the shop. But here we have just a warehouse, right? And then the delivery goes straight away to the customer home. So what is the Hive? Right, and why I talk about it. So the Hive is a three-dimensional storage facility where we store, collect by these robots that are moving on top of this grid and brought to the packing stations. So this grid is three-dimensional. It can be sized in different scales and ways. So it can be applicable for small warehouses, can be applicable for large warehouses. So the biggest grid that we have is located in London, and I think it has mistaken hundreds of robots, maybe 400, 500 robots, if not more. Maybe I'm mistaken here, but the number is huge. And we have two of such grids next to each other. So one grid would be for ambient temperature. The other grid is for chill temperature. So where the products that go in the fridge go, right? And the robots are coordinated independently, so they're not aware of each other, but they're coordinated from the top. And here you can see the way we simulate and model our grid, because it's a complex system. And before releasing it, we need to understand what's the optimal amount of robots that can go on the grid, what are the operational conditions which we can set, what are the faults and what are the possible faults, so to model and create all the possible faults that can happen with those robots. So you can see on the left-hand side is our old generation warehouse, where everything was operating with a conveyor belt. So in this case, you need much more land, much more space. So we have created that simulation after the warehouse was built because it was an old technology. Then we wanted also to analyze how things are working. And in its turn, for the new warehouse, first we created a digital twin, we created a model, we have evaluated different conditions, and only then we build a warehouse. And we still do it to this day. So we would create a grid in a simulation, we create a twin, evaluate conditions, and only then build the actual warehouse. Okay, and now I would like to move on to our most advanced product that is already operational in many warehouses in UK. And we call it on-grid robotic pick. So effectively, previously, the customer items which were picked up by those robots would be packed on a human stations. But in this solution, some of the items are packed already by the robots on top of the grid directly. So like this, we save even more space. On time, the order is being prepared, and we use some telemanipulation to control those stations, and we use a lot of machine learning also to understand how to grasp the items and how to pick, right? So these are the stations that are on top of the grid, as you can see in this video better, right? So this is the robot is moving. So the robots that are on the grid, there's the washing machines, I call them washing machines. So they come, they deliver a storage container with an item, and then the robotic arm would directly go there and pick for the customer. But why we are here, why we still do research, why we're so interested in robotics, the reason lies behind the need to grasp a large variety of items. So we sell anything that you find in a supermarket. Everything has a different packaging, there are objects with different properties, and there is a need to create sophisticated manipulation capabilities that are handling different types of items, right? So, for example, the bag of crisps needs to be handled very differently to an avocado, which is easily bruisable. Or sometimes we have a vision challenge. There might be mix of different teas in the storage store, then we need to understand which one to pick, because there are such a fine differences in packaging from producers. In addition, packaging is always changing, so we can't control what the distributors are providing us. The marketing might change, and they come up with completely different design. So what this means that we need to handle any general object. So this is our challenge, to handle absolutely everything. And this is possible to some extent. So we do use robots, but we can't yet handle everything. Okay, so that's why we get involved. So we do a lot of internal research, and we find a great value of involving in the research projects. And this is my area where I work. So I'll tell you a little bit about the past research projects that we've been involved with, and also some of the current ones that we are working. So this project is covering soft robotic manipulation. So we work with different soft grippers, and we target items that are easily damageable. And moreover, when we do it, we look at the environment that we are grasping with, because we are presented. So these are the top views of the storage containers that we can have in the grid, in the scenario. So we are handling items that are very scattered, items that are relatively easy to pick, and also items that are tightly packed with maybe very few gaps between them. And here we exploit the environmental conditions. So if we have a wall, we can use a wall to push an object against it so that we have a better quality of grasp, right? And so we created these scenarios. So the top 3 rows, these are the 3D printed objects, so the emulated objects, and at the bottom you can see the representation how it is in the warehouse, how it is coming to us from a distributor. And we had all these different robotic hands provided by the partners from across Europe. So the project was coordinated by University of Berlin, Technical University of Berlin, and there is a first hand followed by them, and then there are some hands from Pisa. Maybe you've seen some of them. So these are the grippers that we tested, and in the course of a project, we went through several iterations of this hardware and performed benchmarking and evaluation. So in our work, when we come towards production, towards research that is needs to be applied to a product, it's very important to have a robust way to evaluate any component, especially hardware, that will be put on the industrial system. So we come up with a benchmarking, we identify the criteria that need to be tested, and then we look at the performance. So it's not, of course, at the end of the day, we try to optimize in terms of time and in terms of quality, right? But in some cases, before you come to that, we need also to look at the robustness, to look at the aperture, what type of objects are possible to grasp. So there are many things that we need to evaluate and to look, right? So, and here what we did in our evaluation, we just we changed the approach angle, and we looked what are the best ways to grasp the objects with those hands. And maybe there is a gripper that allows us with relatively easy change of orientation to grasp multiple items efficiently. And this is just shows us final demonstration, very speed up, right? So because it's a research project, we absolutely understand that we can't go with high speeds, we can't go with high. And this is the, so you can see how we're exploiting the environment here for different types of grasping in order to form different relations with them, right? And then eventually we'll clear out the whole storage container. Okay. Then we also engaged in collaborative robotics. So creating a robot assistant that would be able to, let's say, to work in our warehouse and help us with performance of some of the maintenance, right? So this is a project that I have coordinated to work towards the end of it. A little bit of a baby, but I'm glad that baby graduated. So, and here, so you can see the task example. So the technician would come to the conveyor belt. In some of the cases, you might have still conveyor belt system, right? Unscrew the bottom lid. Then he needs to perform some cleaning operation inside the conveyor belt, and then mount the lid back. And in this case, you need to provide assistance to a human. And in order to provide this assistance, you need to understand the intention. And when you understand the intention, there are more challenges because the operation is not scripted. You are dealing with a human. So this means there might be uncertainties, unexpected events. There might be situations that go out of control. And the robot needs to take into account all those situations and also provide help proactively. So this is what we worked on. And here is a little demonstrator, which hopefully loads, right? So here we remove the top lid, then the robot goes. I can see Giorgio went away because this is something similar that will happen in Sestosenso project in one of the use cases, right? And then robot is moving, so lead the manipulation operation, adjusting its grasp in order to have a better stability, helps the human placement, right? And then it continues, right? And then the robot can also help to bring some cleaning materials, assist, etc. And you can give commands with a voice, or the robot can recognize the activity based on visual perception. So now I will move to some of the projects that we work on now. And again, we still are interested in advanced manipulation capabilities to expand the range effectively of items that we can handle. Okay? So first project, so it is coordinated by University of Bologna, right? So this is Intelligent project, and there we try to understand how can a robot efficiently learn to manipulate in a purposeful and highly performant way. So in that project, there are several use cases. So use cases are the example scenarios inspired by the industrial cases where we test the technology and innovation on, right? So we, from Ocado side, we are looking at manipulation of fragile, loose, unpackaged fruits and vegetables, right? So when you need to handle individual items, or maybe when you want to handle multiple smaller items at the same time and pack an order, let's say, in a designated pallet, right? Maybe customers are ordering, I don't know, 200 grams of Brussels sprouts, then the robot would need to provide order on demand. Similar, like when we go to a physical supermarket, we select our fruits, we select certain amount of fruits. So this capability potentially implemented to be online a supermarket as well. Then there is a use case of kitchen scenario. And the use case where we assemble flexible wires into safety connectors for automotive. Okay, so yeah, one more time. So looking at our use case in details. So why it's complicated? Well, because first of all, the environment is very dense. The items that we're dealing with, they are of high variability. So we have different sizes of items. We have different stiffness of items. So might be very easy to damage some items, and some items might be rigid, right? So we need to consider, because at the end of the day, we want to deliver to the customer undamaged goods of a good quality, right? So here the damage is absolutely unacceptable. And as we do in many projects, in a lot of research, we are looking at the way humans are performing operations. And then by looking at this, we can understand what are the most efficient strategies, what are the most effective strategies that humans can implement. And here particularly we have noticed that using how people are differentiating from grasping individual item one by one, or maybe grasping multiple items together, right? So there are different strategies that can be used and which we are learning from. And based on that, we don't only design our grasping approach, we also design the hardware that we're using. So the hardware can be inspired by the way humans are doing things. So we don't aim to replicate a human hand, but we aim to replicate the capabilities of a human manipulation skills. Okay? And here, so the project is ongoing, right? So this is initial prototype, so which we have created. So the gripper is designed by University of Genova, Giovanni Barselli, right? So that's the gripper. And here, one of the examples, we are looking how, with maybe limited tactile perception capabilities, we can grasp multiple items. The next stage would be to understand how can we reduce this damage, right? So, and then we perform different tests which help us, as I said, to understand how the criteria and key performance indicators are implemented for the different scenarios, for the different hardware configuration. Okay, right. So this is this project, and yeah. So the next project is called Softenable, right? So here we look how to manipulate things, but we look at the challenge of manipulating flexible objects, right? So when it's a rigid object, we have certainty. Even if we don't know the model of an object, we can still relatively easy to predict the motion of it inside the gripper. But if we are dealing with items such, let's say, fish, meat, anything that is deforms unpredictably, anything that has different stiffness qualities, we need to have a different manipulation strategy. And here exactly, so this project is for 4 years. Fish similar items. This is one use case, and there's another use case. We look at the hospital scenario when nurses need to handle personal protective equipment. So before the surgery, they would prepare piles of personal protective equipment, and then they hand it to the dressing up stage for the clinicians and for the nurses. And the operation is very repetitive and also requires manipulation of highly flexible items. So this is something statistic. So research center in University of London. I'm not sure that's the correct name, right? Is trying to do. So how to manipulate those flows, right? And then we look at understanding, grasping taxonomies, understanding what are the manipulation primitives, looking at the design of the grippers to understand what are the design features that we need to implement to grasp those items, right? How can we fixate them inside grippers? So it's quite a project, little amount of partners, but with very high ambitious goals, right? So there is not only grasping there, then placement comes in terms, because, for example, if you have a tray that you're packaging for customers, there are certain rules how you pack your fish, let's say. So fish should go with the skin on one side, with flesh on another side. If you want to put the second one, you can't overlay the two because you contaminate flesh. So, and then you need to control your place in space. So there comes in mind the control of the shape of the fish. And this depends on the way you grasp. So there are many things we take into account, which we are addressing in this project. Okay? And here comes the Sestosenso project, so the project we're all working on. So that's why we've had a meeting here. And here we look at manipulation of large items that are coming into our inbound, right? So these are the items that are coming from the delivery lorries into the inbound area, and then they are loaded into the grid, right? So this is the items are coming before, and then they need to be unpacked, unwrapped, unloaded from the pallet and placed inside the grid. And we look at the bimanual whole body manipulation, and we are very keen to try different sensing technologies and to see how the application of tactile skin and other modalities of sensing, such as proximity, can help us to improve the control we are developing for the robot. And this is the example, just the things from the warehouse. There are absolutely different shapes of objects. Things can be rigid, maybe things can be heavy, or we can have objects that are articulated inside. So, for example, on this bag of potatoes, right? So the objects are the potato would move inside. So you don't have a stable item to manipulate. You need to control the dynamics with two robotic arms, which is quite a challenge on its own, even for a person if we have a very heavy bag and we need to manipulate it with our two arms. Okay, and so looking at the system requirements, right? So again, we performed some studies of human grasping, trying to understand how humans are doing things, what are the challenges, what are the strategies. So humans might be lifting something, rotating objects. When we pack, we might be sliding an item, we might be rearranging. So these are all the things that we need to take into account. And in addition, so the system should be reactive and compliant. We should be able to handle heavy things. As I said, we need a multiple point contact to our life and environment, because we did conduct some tests. And absolutely always, without any perception of the environment, we can't handle anything that is deformable, anything that is fragile, and essentially not a virtual solid block, right? So because we will be damaging, we might be losing and dropping items. Okay, and there are some questions we need to answer, right? So how can we determine those kind of contact points? Sometimes we might have a sensor available, sometimes we might miss sense, how to propagate this and predict, and how to handle the unreliable performance from sensors, because it is hardware. Sometimes, even if the sensor is good, all the time we have some deterioration of signal, we have some damages. So how to detect that and how to understand when it's time, say, maybe to change the sensor or adapt your control strategy to the appropriate sensor signal. And again, we look at safety, how to understand if a contact is expected, is an object, or unexpected. Maybe the robot is working in a collaborative environment, human, whom we need to detect. So there are many things which we take into account. And I think that's it from my side, right? And if you have any questions, I would be very happy to answer. Yes.
In the gripper, the one that like your do you have tactile perception there, or it's just like compliance? So
That's just exploiting the compliance of the gripper together with environmental constraints. So we didn't put any sensor.
I have a question. In the previous slides, you mentioned that you use this sort of detail that these boxes have like walls. So you can use this function of pushing the objects to then pick them up. So maybe you could elaborate how you implement these types of functions.
Yes, so this is part of our planning, right? And so we would design a planner that take first different repertoire, and then based on the sensor information from the environment, so we can use, for example, we have a scene where we place items, right? We would have a camera which would have a point cloud, which will so we can see some gaps, right, in the scene. We can have also our proximity sensor on the wrist of the hand to explore the environment, so to enhance the understanding from the robot perspective, so all those gaps, right? And then the controller, let's say, the planner would recognize the gap in the scene, and then it would send a signal to the controller to implement specific action, right? So you need to create a planner, right? And then you need to send a command to get your sensor information and send a command to the controller to implement a certain type of action.
So you have like a preset set of actions that you can use.
Yeah.
And then the usage of them depends on the sensor detection, right?
Yes, so there are different ways to do that. In this case, we use a repertoire, but we can, of course, use also machine learning technique, reinforcement learning, for example, where we still need to get sensor information, right? We might get the RGBD information, right, of the environment, and then the robot network would analyze this scene and would implement a certain action which is learned from a previous demonstration, from previous training. So there are different ways to do it. Just because this project will focus on sensing, we use a repertoire of actions.
Do you have some real life example in Ocado where sensorization of your robots are helping to improve your efficiency?
I can say that we work internally on a lot of different sensing technologies, right? So we use vision extensively, right? So we rely on vision in production. Of course, we have cameras, right? We use depth information, we use visual information. There are some other sensors available. You know, we can't operate in the environment without physical perception of that environment, because we operate with many items, and sometimes it's impossible to handle something without understanding the forces we need to.
How can you foresee for the future, for example, now these research projects on a tactile sensing, for example, can you foresee that it can really help? Absolutely.
Yes. So a lot of things that we do, we might be also doing internally, right? So we work internally on some of the tactile solutions, right? So we take from different university sensors and we test them, right? So this is a big ongoing work, which we definitely know is required, and I think the whole robotics community knows that you can't have a gripper without a sensor, right? And I think it's pretty, you need to understand the environment, unless maybe you use some soft robotics approach, right? Where you are inherently compliant with wrapping around the items. It's slightly different, but still need sensing.
Questions? Okay, then thank you very much. The next talk here will be given by Alessandro Albini. He is a postdoctoral researcher at the University of Oxford. He earned his PhD in robotics on autonomous systems from the University of Genova, and has already quite a long experience with the development of large areas, tactile sensing. The talk will be about tactile perception for robotic manipulation, learning, and control. So it is yours.
Thank you for this introduction and for having me here. So, in this talk, I will explain my research started with my PhD in tactile perception. So, okay, some information about me. I got my PhD at the University of Genova in 2020 when I worked on the area of tactile sensing for robots, so whole body sensing applied to human robot interaction and control of robot. Then after the PhD, I moved to Oxford when I started working also on soft robotics, and now I'm basically 100% working on the Sestosenso project where we are trying to embed tactile and proximity sensing. So, okay, that's basically the outline of my talk here. I would like to start by saying why tactile sensing is important for robots. And so, okay, I like this video. This is a very old video. So the robot that you can see there, it's called Unimate. It was the first industrial robot ever commercialized. So we are talking about 1960. And it was, I mean, groundbreaking at the time, no? And few years later, the company released this video. So they were showing their vision of the future. Now they were saying in 40 years, that's what will the future look like. You know? We robots are going to share the environment with the humans, supporting them in everyday life tasks. So now it's about 60 years from this video, and I think no one has such a kind of machine. No? Yeah. So which was the problem? No? Well, we were very good at. So we approached the problem as an engineer. So we had a task, and we were very good at making robots solving specifically that task. So you can see some example here. So robotics was very successful in industrial tasks like assembly lines, where you have just one single task. There is no uncertainty. You always repeat the same movement. But actually, these robots are not so human friendly. Usually, they are kind of constrained in cage to keep them separate from human because they are dangerous. Other example, where if we take, for example, the vacuum cleaner robot, again, one single task, it can deal with some degree of uncertainty, but if your furniture is not arranged so well, you need to make a room for the robot to be able to clean. So what's the problem? So sharing the human workspace is very challenging. So how do we move from this environment, so like industrial setting, which are very constrained, well defined, where everything is repeatable, to our world, which is messy by definition. So, and we are asking a robot to perform not just one, but a wide variety of tasks in an environment which is uncertain. And so it's likely that robots gonna collide with environment and with humans. So we need ways to manage the collision in a safe manner. And if we look at how can we do it, and if we take a human as an example, we primarily using the sense of touch to deal with manipulation, grasping, collision detection and reaction, but we also use it for exploring objects and also to interact with objects, sometimes using the whole body. And so I mean, the thing's very simple. If it's useful for human, it would be also for robots. And that's my research. Since I started the PhD, I tried to use tactile sensing, whole body sensing to transfer this skill to robots. I worked on contact detection, reaction, human-robot collaboration, exploration, classification, and so on and so forth. So I'm gonna give you like an overview of some of this aspect in this talk. So first, just to clarify, what is a tactile sensor? So in this talk, what I mean for tactile sensor, because tactile sensing is multimodal, and here I'm just referring to devices capable of measuring a force of pressure distribution. That's more or less how they look like. So you have like a soft material, you apply a force on it, and you have on the bottom some kind of transductor that basically indirectly measure this pressure distribution. You can have capacitive sensor, So basically the green element that you can see there is a positive plate of the capacitor. And if you have like a ground plane on top of the former, you can just measure the difference in capacitance. And when the two plates are getting closer, and you can associate that to a pressure distribution. Same for another type of sensor, camera-based sensor. So I place a camera on the bottom and I can use actually the camera. So from the image, you can reconstruct the deformation of the surface. So, and that's there you can see an example of the output that you can get. And of course, this can be scaled. Maybe Giorgio, we're going to talk about the challenges of scaling from small area to large area. So large area body tactile sensor skin, how do we call it, are basically tactile sensors that can cover possibly the whole robot body. And that's the kind of output that you can see that that's the side skin, a skin that was developed by the University of Genova. Here you can see the type of output you can get. So we can get the precise contact location, the whole pressure distribution. You are able to measure multiple contact forces, and so on and so forth. So how can we use this skin? So, well, there are many applications, so they can be related to safety. Of course, if you have whole body sensing, you can detect forces and maybe stop the robot or react. We can use them to allow a robot to execute tasks possibly without destroying the environment surrounding the robot. And we can use it also, of course, to interact physically with humans. Now I just want to talk about the first point. So how can we use skin for safety and control of robot? And the idea here is, so we want the robot to execute tasks in a constrained environment. Can you imagine, for example, the environment Lisa showed before, where maybe the robot has to perform a task and there could be obstacle in the middle. So we tested this. So we created this scenario where here you can see the black part is the one covered with tactile sensors. And so the idea was that the robot has to reach some target location with some obstacle in the middle. So here, the idea was that the robot was blind in the sense that there was no vision. We just gave the target point and we asked the robot to reach them. And we used the skin to basically feel, so reconstruct, perceive which were the contact point and the forces on the robot. And we basically set up this control pipeline where we were trying to minimize the contact forces while reaching the target. So basically the fact is the robot can accomplish the task without basically destroying the environment. Okay, this, so for what concern human-robot interaction, so a few years ago, during the PhD, I was involved in this European project, Collaborate. And so one of the use cases was related to a manufacturing environment where an operator had to perform assembly operation in close to the robot, basically assembly operation on a windshield of a Maserati car. And the idea was that there would have been a robot supporting the operator, like, let me say, unloading from the weight of the windshield. And the operator had to move in a kind of ergonomic way the windshield, depending on the type of operation that he had to perform. And here the problem was, how can we provide a smooth operation? And one idea was, okay, we can use tactile sensing to enable the motion of the robot. The problem was that you cannot just say, okay, if I'm touching, just move. Because in this kind of operation, there could be, so maybe the human can collide with the sensitive part. So we needed a way, some processing to understand if the human was applying a kind of purposive interaction. So, and the assumption that we made at the time, we say, okay, if I want generally interact with something, I use my hand, so I am approaching it with the hand. And we try basically to process the sensor data to recognize the pressure distribution that was applied by the human hand, and actually assuming it that was coming from a purposive interaction. So we tested it in this setup. So we use the same robot, we cover the forearm, we set up this processing pipeline where I think Okay, I made a mistake with the slide. So the idea is that we have this sensor covering like a 3D shape. We perform some geometric transformation to make it flat, and we convert it to an image. One image simply because there were classifiers for images, so we had a lot of state-of-the-art tool to process and classify images that basically work in 3D. So we decided to basically apply this set of geometric transformation to transform the input data to this flat distribution. We involved a lot of people so we collected this data set. We asked a lot of people to interact in different ways on the robot to make sure that the classifier is able to generalize with respect to different human different and size. And we also took another data set which basically was everything else but human hands. So at the end, we trained this network. We were able to transfer it to the different geometries. So that's the final setup. There were like handles covered with skin at the corner of the windshield. There you can see the operator that when you're willing to interact, we just apply the force with the hand and he's going to move it. So on this aspect, as you can see, actually to process tactile data, we use the images, but it involves a set of operations. So for example, here you can see that I have the geometry, which is not flat, so 3D. So I have to first, if I want to, for example, to extract the contours of that contact shape, I have first to make it flat, then to perform an interpolation, create the image, process the image, come back to the 2D domain and come back to the 3D domain. So we wanted to find a way to avoid to use this complex process pipeline. So what we explored was basically the use of a sort of mesh convolution based on mesh. So we could have directly process the output of the skin as it is without making any transformation. So basically, what in this case, by changing the weight of the filter, we can implement an high-pass filter directly in 3D and basically extract the contour. And in this case, we were asking the robot to follow the mark. So now, okay, for the last part of the talk, I wanted to talk about some of the work that I'm doing since I joined Oxford with Professor Maiorino. So we were interested also in understanding how the body is affecting the tactile responses. So what's the role of the body in that? So we designed this soft hand. It's a pneumatic hand. The white pad that you can see there are tactile sensors. So in this case, they work in this way. So you have a hollow chamber, and which is filled with air at atmospheric pressure. You have a pressure sensor on the back. When you pass on one of the white pads, they detect the variation with respect to atmospheric pressure, and again, you can associate it to a pressure distribution. So as you can see, the hand is compared, so it's conforming to the objects, and the control that we are applying is quite easy. So you adjust, so every chamber is connected to the same pipe where we can just suck the air, and the hand is going to conform to the object. So in this case, we're interested. So as you can see, depending on how the hand is touching the robot, this is going to get to a different tactile signal that you can see there in the activation part. So we thought that this could have been useful to make object recognition. So we set up this pipeline where basically we went. The video stopped. Okay, so we set this learning pipeline iteratively where the robot, by increasing the number of grasps, is increasing the knowledge or the confidence in the object recognition. So you can see that at the first grasp, the robot is confused between one or two objects, and then by increasing the number of grasps, you can get higher and higher confidence. So you can apply this process how many times as you wish. So, and just stop when you have a certain confidence. So Of course, we are using a lot of machine learning to do this task here, this type of task here, but actually there is a catch. So tactile data collection is quite hard. So because we need physical interaction, and this is time consuming. So if we imagine like an object recognition task, every time, so if we want to explore the whole object, we need to basically cover all the surface. And this is a problem also because the way I interact with the object change the response. If I less so much force, if I rub on the surface with respect of having a static contact. So that's a problem. And usually to do that, I need a controlled machine, so a robot to do it. And sometimes the full exploration of the object is not possible. Imagine, so for example, if I cannot use that sensor to get inside the mug because it's too big. So it depends also on the geometry of the sensor. So we started with the idea of, okay, can we find ways to train object classifier which are easier, or maybe exploiting other modalities. So this is the classical pipeline that you have for object recognition. So this kind of state of the art. So you have some object, you take some data, you create a representation of the object, images, for example, whatsoever, and you just feed a classifier, you train this classifier. So what we were start to investigate was to use cross-model classification. So what does it mean? That I still have a classifier that can make prediction on tactile data, but I want to train it using modalities which are easier to acquire. So for example, vision. So the idea is that I'm using vision, I train this model, and this model must perform in the same way if fed with tactile data. And of course, so since we don't want to explore the whole object at classification time, this should work also using partial representation of tactile senses. So for example, you can imagine, so I'm looking at this table, I have the model of it, so I reconstruct it. Well, when I touch it, I don't need to explore the full table, so I just need some feature, right, to recognize it. And so that was the purpose of this work. So, okay, this is the overall training pipeline. So what was interesting here that to make the model to be robust with respect to this, we at training time, we set up this curriculum training pipeline where basically by increasing the number of epochs, we were reducing the number of points in the visual point. So actually we were feeding other samples. And this is the type of result that we got. So you see that using 40% of the points of the tactile point cloud, we were reaching almost 90% of accuracy, and we were able to get to 100% using 60%. Okay, so I want to conclude with this last work. So previously, we were using cross modality to perform object classification. So the idea here was slightly different. So instead of recognizing the object, we want to generate using images the type of the tactile response directly. So imagine that you take a picture or you get the depth map of a point on the surface, for example, that like the gear on the turtle. And what we want to do is to artificially generate the response that I would have obtained by physically touching with the tactile sense. So to do this, we basically, the idea was that we first trained a system in simulation by taking paired depth map and tactile responses of a camera-based sensor. We took a huge data set and we trained this generative model, and we brought it to the real world. So in the real world, what we did is that we used a camera to create basically an F model, which is like a volumetric representation of the object. So we can query some points, so we can generate the equivalent tactile response that we would have obtained by touching. So there you can see some example. It works quite well. So we needed to solve some sim-to-real gap by applying some processing. But there you can see that the difference between the generated output and the real output that we took with the real sensor are very minimal. And okay, I think this is all. I want to thank all the collaborators that participated on this work activities. And okay, that's the outline of the talk. If you have any questions, thank you.
Can I ask a question?
Yeah.
So, how much it costs to sensorize the size changes on the robot?
Yeah, cost in terms of what? No, because there are two costs: actually the hardware and the time they took to do it.
The cost of the hardware.
Okay, the cost of the hardware. Giorgio, how much did you pay for the skin?
So, yeah, if it depends on the market of the chips and on the capabilities of the service to manufacture multi-layer and flexible PCBs. So let me say that the higher cost is the PCB. The chips are a couple of dollars, less than €2. These are quoted before the Sestosenso project. In the Sestosenso project, we are exploring solutions which might reduce the cost. One of them is printed electronics, because we think that besides the fact that there are different technologies under development, different things, but we are using polyimide. Polyimide is horribly expensive. Copper laminated polyimide is dramatically expensive. Processing and manufacturing multi-layer PCB, it's expensive. So
in that implementation, there were like 3,000 sensors, something like that. Then apart from the cost of the PCB and everything, there is the cost of the integration. Right now, it's still perform manually, and took me a couple of months to do the test. It's not just the cost of the hardware. It's, if you want to scale, you also have to consider the cost of the people. So
yeah,
actually,
this is
that's the biggest cost.
got the integration, the cost of integration.
What is energy consumption of such a tactile skin?
We for the arm, so the implementation you can see there, I was powering with an USB. So it was actually the USB is the standard one, should be like 5 watts, something like that. So it's like 500 milliamps at 5 volts. So no, 2.5. So actually, but it was enough to power of that of the skin.
The power is not of the transaction, it's on the computation side.
Basically, yeah. It's just the
So capacitance to digital converter.
actually that it was
I'm not.
it was powered with USB 2.0. So actually it was 500 milliamps, 5 volts. So but it was able to manage.
In the example where you showed the robot is working in this environment where it has to go through different objects, this tactile skin is connected with a robot controller, so he is deciding.
Yeah, basically, basically no, it's not deciding where to go in the sense that the skin is detecting the forces and is deciding how to move to minimize the forces. So actually it's closed loop in the controller. It's feeding the controller in closed loop. And so there is one kind of task objective to say, go to two other points. and that there is a closed loop part using the scheme that say try to do it by avoiding to destroy the environment. It means move in order to minimize the contact forces. So it's done actively. So yeah, it's not just passive compliance. It's saying, okay, move actively, we will reduce. Yeah.
If I understood correctly, for training on the synthetic data, you were still generating it from real world data, correct?
No, we trained it in simulation. The data that we took in real world was just for validation. So we did as a comparison to have a benchmark, because otherwise we wouldn't have any data to compare it. So
the set for training was completely synthetic.
yeah, it was simulation. Actually, I'm not sure to remember the timing, but to basically generate the data set in the real world. So actually all the procedure that's taking the camera, creating the volumetric representation took like 20 minutes, while taking the images to have as a benchmark. So that the tactile data to as a benchmark was like more than 4 hours. In a very simplistic scenario, so just up and down. If you use like complex object, okay, it's going to increase the complexity much more.
Yeah. And maybe I missed it, but how did the precision compare?
Sorry?
If maybe I missed in your presentation, but how did the precision compare?
No, we use the linear point metric, but basically we use the standard metrics for image to image. For image to image translation in generative models. So we evaluate the accuracy, the similarity score, and so on. They were helpful. Actually, there are other works doing this. The accuracy were comparable in some sense, but the scenario that we targeted was much more complex in the sense that usually this is done with flat objects to the object. Here we addressed complex object with complex features.
What is the force resolution for these sensors? It's in bits, or?
The capacitance to digital converter is 16 bits, but I remember from the characterization experiment that we built it, each each capacitor can read up to 10 Newton, just the single taxon. But usually, since you have larger contact area, it will be spread, so you don't easily saturate.
About the project collaborative. Can you explain better how this tactile skin integration was helping to collaborate? That keeps the windshield.
Yeah, because the idea was there was the robot holding the windshield, and we wanted to find a way to smoothly interact with the robot. Smoothly means that usually these things maybe require the operator to push a button, move the robot, push another button to stop the robot, and so on and so forth. We wanted to find one of the goals of the project was actually to try to make this cooperation smooth. And usually, when you want to interact with something, you just grab and move the screen. You try to use the sense of touch in space. We were thinking that actually that would have been much more smooth for the operator with respect using like gesture, maybe just buttons. And the problem was that there would be also collision, so you cannot just say if you detect a contact, just move the robot, because maybe during the assembly operation, the operator using the body or head would have hit the sensitive part, and in the case the robot would have moved. That this is not what we wanted. It could have been potentially unsafe.
The projected is two handles.
Yeah.
That the operator is working always with two hands.
Yeah, the handles are at the skin there. So what we did, so the robot has to understand when the interaction was positive. And what we did was to basically do classification on the pressure distribution of the light.
So now we have the last talk by Professor Giorgio Cannata from the University of Genova about robots, touching and touching robots. He is a full professor at the University of Genova. His research interests are broad: robotics, mechatronics, soft robotics, also bio-inspired robotics, underwater manipulation, and tactile based robotics. He was coordinating several projects as well as Sestosenso, which we are presenting here. And he is also coordinator of the Italian doctorate program in robotics and intelligent guide. So the floor is yours.
Most of the things that I'm going to talk about have been already presented. So I'll try to be the complement too. And it's Friday, it's late, so I'll try to be short as possible. So just let me introduce. My name is Giorgio Cannata. I'm professor at the University of Genova. Yes, here it is. Italian North Riviera, okay. Nice place, about 500,000 persons live there. The University of Genova, it's pretty old. We are a medium large sized university. About 1,300 faculty members. We have a strange system, so we are encapsulated into departments linked together, and we are borrowed to the 5 schools of the faculty. We have about 30,000 students which are allocated to the schools. The university has 4 main sites. I'm in Genova, which is the main site of the university at the Polytechnic School of Engineering and Architecture. I'm part of the DBRIS, which is a department keeping together computer science, bioengineering, robotics, and system engineer. I am an electronic engineer who made for most of his life automatic control stuff. And at some point, I'm a fan of robotics. At some point, I restarted doing a bit of engineering, and the things that Alessandro presented are in part are the outcome of that. So the department has a turnaround, which is about 3.5 million euros. These figures are a bit old, but on average, let me say, before Next Gen EU, these were the figures. Now we have a lot of money that we cannot spend, so it's a strange situation. We are rich, but we cannot spend money. Don't ask me why, but this is the situation. This is where we get the budget, European project, and Sestosenso is a very nice initiative. I'm glad to be there, not just because I'm coordinating this bunch of crazy people, but no, it's great. It's great. In the department, we have a group specifically working on robotics and intelligent robotic systems. And embedded within the department, we have an international master on robotics, which is part of the course of robotics engineering. And this has been a great initiative. It's almost 17 years that is running. We have students from all the parts of the world. And we have also, and this is a pretty strange situation, we have also 2 PhD programs in robotics. This is the old one. I've been the infamous coordinator for 7 years of this. This is a PhD program which is shared with the Italian Institute of Technology, which is based in Genova as well. And from 2022, I am the coordinator of the Italian doctorate in robotics and intelligent machines. I'm saying this not because I am the coordinator, but because this is a quite interesting initiative, which was the idea was to create a community of students working specifically on problems related to robotics. It's a consortium of 27 among university and research centers all over Italy. And this was the opportunity to bring together students working in all the domains related to robotics. We have students working on the legal aspects. We have activities related to legal, ethical, and societal aspects connected to the robotics. I'm saying this because we belong to different domains. You're scientists, we are engineers, and maybe since we are working on robotic projects, maybe there could be the opportunity for exchanging students and sharing projects at PhD level within this framework, because I think this is it's a growing community. We are starting in these days. The calls are open for the third year. The robotics and autonomous groups is formed by nine. Yes, we had a new entry a few months ago. Nine people. We are working. Most of us are coming from the automatic control community. So we are working in control of robots, human-robot interaction, and Alessandro has already spoke about that. Autonomous system, underwater robots, application of AI for social interaction and other technicalities. One of them is mechatronics, which is part of my work. Sestosenso is one of the projects that we have coordinated over the past 12 years. RoboSkin is another one that I had the chance to coordinate, and where all the things you are seeing today and that have been presented before by Alessandro have been originated. And these are just a few examples of experiences that have been done by the various people working. So you have problems of cooperative robotics, underwater robotics, space robotics. We had for a quite long time a connection with Thales Alenia Space, and the other core business is in underwater robotics, and I worked on dynamic robot control and strange mechatronics application like bio-inspired robotics and so on. This is the introduction. I will move a bit faster. Why robotics? Because, and this is interesting because I grew up with the idea that the robots are somewhere far from humans, but the idea is that the robots should be close to humans, and in fact, I will talk again. I will repeat the lecture, but the problem is human-robot cooperation. one way or the other. This is what is interesting. Just a few figures. Robots are a business. The market is growing despite the COVID pandemics and so on, and it's great. It's growing at a reasonable rate. Okay, forget the China, Europe. No, China is okay. Forget it. I'm talking about Italy, but you should consider Europe. It's a good market. So there are opportunities. I say forget China because 25 years ago, China was not there. So they are aliens I'm saying in a sympathetic way, but okay, they are absolutely outliers. Okay, these are the old vision of the robots. Now, the idea is to have definitely much more suggestive ideas. Humanoids, and I will return on that, are here. Machines for handling cows are products. They are no more research. They are getting to the market faster and faster. And this is an interesting point. So I said robots are getting closer and closer to humans, and also the market is following this trend. And this is the share of Europe in the market of service robots. This is important because, okay, I pretend to be a researcher, but I'm a teacher, and we are trying to create engineers and people who could make business out of their engineering and technical skills. So at this point, Europe is leader, is definitely leader worldwide. And these are the new scenarios. One, when I said there is China and there is a return to Europe. How? By thinking a different way of producing things where the persons collaborate or cooperate with the humans. The two videos on the right-hand side are demos from a project that was quoted by Alessandro before, where a few of us were partners, where we showed the possibility of improving the manufacturing capabilities when the robot is sharing its action with the expertise of humans. This is the market of the cobots. The market of the cobots is growing at twice the speed of the growth of the market of the standard industrial robots. So in a sense, it's not just a motivation ground on curiosity. There is a push to introduce new technologies, and again, in Sestosenso, we are struggling to find solutions which are cost-effective, not just proof of concept, but cost-effective solutions. Cobots are things that I'd like to have at home. So the idea of the robot market is something which is not just related to the manufacturing side, to the industrial aspect, but it's going to become the next car. Maybe you are willing to pay, I don't know, 25,000 euros for a car. I personally would like to pay the same money for a 24/7 device that take care of my house. So I think we should start thinking of the robots and the cobots in this sense. And so besides service, besides domestic, I think that there is another important aspect which is related to cobot, to the fact that we are getting older and older on average. But I'm almost at 61, and I don't feel to be placed aside. So people have expertise, but maybe they are not as strong as young people. So thinking of a production where expertise can be some way used by transferring the effort to the machine and using the cognitive capabilities of people as a social impact. Because in this way, people can keep on producing value. Keep on producing value means that social insurance, social costs could decrease. And you could guarantee on average, a better environment for the population. So these are not specifically technical comments, but again, these are some of the motivations. Now, I was a fan of tactile sensing for many years. Why? Because there are okay, playing music, it's a tactile problem. There are some aspects of manipulation to grasp an heavy object. You use your full body, and this is one of the ideas within the Sestosenso project. But there are other less immediate aspects which are related to social interaction. So we touch people, and the touch is conveying in some way is conveying information. This was an experiment that was done within the European project Robotics about 12 years ago, and that puppet was built to enforce the capability of interaction of children with autism syndrome to learn to socialize. And it was, I mean, I'm definitely not an expert, but touching the robot and getting a feedback from the robot itself, which felt that the touch with the children was a way to trigger an interaction also with the other people surrounding the present in the scene. There is a side effect. I started working on tactile sensing for underwater stuff. I would say almost 30 years ago. In the past 20 years, the production, the paper on the subject skyrocketed. And okay, so this means that there is an interest. As Alessandro was saying before, there is an interest, but you cannot buy skin for robots because it's hard. It's still not an easy task. So in 2006, we invented this idea, which is it's a modular system which solves quite many of the problems that there are to build things which are large. And I mean, the idea was simple at the time. Today is obvious. It's networking. So we developed a network of embedded computers, and that idea was applied in different type of situations. Let me see. Please start. Doesn't start. Okay. Anyway, the video on the right, top right part was already presented by Alessandro. And these are some of examples that we implemented. This guy here, he was a PhD student of mine. He's a computer scientist. I think this is the only time he touched the robot. He stayed in the lab for 3 years. He was an excellent software developer. And at some point he said, I want to build my tactile sensor. So he took a 3D printer, and I call it 4 sensors in a day, because it proved that one day you could design the tactile sensor tailored for the application, and implemented this demo for human robot caresses or whatsoever. The video in the middle bottom lower part is related to another project called Lopema, where again we could transfer the same technology, the same ideas, and okay, over the years we made different types of experience. I'm going to accelerate because the next videos should be familiar now. I just want to add a few things. We are going closer and closer to the concept that we are exploring in Sestosenso. And there is always a duality between vision and touch. And the interesting thing is that vision is, let me use this word, is fast. So you see without doing anything. You lay down on your sofa, switch on the TV, and you see whatever is on the TV. If you want to touch, you must do something. And when I say do something, generate a mechanical interaction. And there are situations where generating the mechanical interaction is fundamental. This is not the room of my daughter, but it could be. And if you enter during night, no vision at all, you need to have a complete tactile sensing from the feet to the hand. So this is, let me say, a trivial example. This is interesting because you can recognize if that truth is right or not just by touching, because the color does not provide anything. And this is again inspiring, and the demo that Alessandro showed before entered the demo of the robot moving across the falls, entered this type of applications. You have a lot of vision to do, but as a matter of fact, you need to move across the plants without damaging. It's not a problem of seeing the plants. It's a problem of generating the correct control action to avoid the damage of the plant. And okay, this is the video that it doesn't work anyway. For some reason, they don't work. But you have already seen that. It's the same movie. But you can easily find the analogy. In that case, large area robot, so every part of the robot is basically sensorized. And what we could prove is that a pure reactive behavior, so without any cognitive action, allowed the robot to navigate within an environment full of toys or full of plants or full of whatsoever. But I think we have already seen. Maybe we can take the video of Alessandro. Doesn't matter, don't worry. I'm going to finish. So this is the side robots touching. And there is a dual situation, and which is the word of the problem of touching robots. Touching robot, it's the real core of the problem of human-robot interaction. And one of the things that we explored, and one of the things that are going to explore again in the next future within the Sestosenso, is to take a man and take an elephant. Okay, I mean a robot, a human killer robot, a very huge industrial robot, and allow them to interact safely. And again, the challenge is to exploit the tactile sensing as a key medium. This is the demo that was shown before, which represent an industrial work cell where the full robot is segregated and the man cannot interact directly with the robot. So why this is a poor scenario? I mean, 3 robots, okay, so there should be some society for that. But the real problem is here, because there's a huge space on the shop floor, which is not used for any purpose, but just for storing components, and you need additional hardware, which is just required to avoid the direct contact with the human. So the things become different if the human and the robot can share the same space. And if this is the case, you save room, and you can give the robot additional functions. So you reduce the usage of space, you reduce the number of components forming the cell, and you can get, when I say you, in this case is Stellantis or Peugeot or whatsoever, it doesn't matter. So which was the idea? And I'm going very fast through. The idea is to give a semantic meaning related to the touch in the human-robot interaction. And I'm going very fast. These are specialization of the demo that was shown before by Alessandro. So we developed these sensorized handles. And this is the idea behind the touch-driven control. In this case, you have a non-compensated robot. So the robot is hit and it can move, in this case in passive form. In this case, the robot is enabled to move only if an eye contact is recognized. You could use a button, yes. You could use a button for that, but that's not the natural way for interacting with the robot. Let me show what happened, and this video was already seen before. This is the general demo that was produced, but you have already seen this video. Let me just say that this guy is an operator from CRF. He entered the lab, he didn't know anything. He just knows his job, which is installing, assembling the parts. He entered, he grabbed the handles, he moved the windshield, which was not a natural task, because in the real environment, the windshield is fixed on a table. So if it starts working at this side because it's comfortable at the beginning of the shift, and after 8 hours, maybe he wants the windshield to be placed in another configuration, he can do. And he can do in a very natural way, without pushing buttons, strange buttons. Actually, he's still pushing a button. Let me show where and why. That robot is a human killer. Okay, it's a robot with a payload of 250 kilograms or so. And you have seen the person is pushing a button. And that button is the trigger for the robot. You can see now again, it's a trigger for the robot to say, okay, you are going to interact with the human. So please move very slowly. But everything in this phase is totally, we say, open loop. There is no feedback. There is no safety in any case. And there is this transition. And in Sestosenso, what we want to explore is how to solve this transition. And so we invented the idea of giving the skin not just the capability of sensing the touch, but to see. And this is the idea of creating a kind of skin vision system. Okay, this is the how to say deadline for the project for Sestosenso. And the technology, it's called here proxy skin. It should be proxy tactile, better called the proxy tactile, because the sensing modality is this. And what we want to do there is to explore the possibility of touching the things without doing anything. And this is one of the very first demos that we built. You can have the idea of how the robot can perceive as an image a person moving around. And these are some of the components that we are going to integrate on a universal robot that will be used in one of the demos. Again, you can see how proximity and touch are managed as equivalent. So you are touching with your gesture. There is no physical interaction until you get a physical contact, but the information that the proxy tactile system provides is a kind of contact, like you know, like the wizard in the magician shows on and so on. Okay, this is a stupid last bit, really stupid, but okay. I always find it's fine. Okay, maybe I'm really stupid. We spoke about people touching robots, but in this game, robots could touch robots. This is a serious part of the game. Why? Because you might have in a setting robots which are programmed or developed independently one from the other, which might, for any reason, share the same space. So sharing the space with a human or sharing the space with another robot might gain benefit by applying the same solutions and the same ideas and the same concept. What you see here, it's not strictly speaking related to this, but I found quite interesting the similarity between the cartoon And that demo, that was a demo during the RoboSkin project, and there was this robot punching the other one. So I'm thinking of robot wars. I mean, boxing or fighting robots as maybe it could be enough. And I'm done. But the very last bit is this one. I said Europe is leading. Please consider that within this share, it's not just a machine. It's the full set of technologies which are enabling. And I'm happy to be here because I enjoyed very much the visit yesterday, and the work on fundamental science of materials, sensors, and so on is a key element. Because we need smarter sensor, low-cost sensors to get to low-cost, versatile, I say plug-and-play machines. Because this is the way I think the world is doing. Why I'm saying this? This is a news from this was an investment of Jeff Bezos. This new is, I think, end of February. Yeah, mid-February this year, 23rd of February. Jeff Bezos and his rich friends have invested $2 billion for developing a human, which means that one way or the other, they want to get money back. Maybe to build soldiers. I'm skeptical because there's too many people that would like to go to the war for money. But I think that this is a kind of, yes, it's a unicorn. Okay, so this is why I think that despite the certainly small added value of our research, maybe yes, maybe no, I don't know, but I think why these are the reasons why investing and putting effort in research and in the formation of young, skilled robot engineers. When I say, I repeat, robot engineers, it's a broad area of competencies which are in. And these are the persons that have worked with me over the years, and some of them are here. And I've been lucky because I learned a lot from them. Maybe they have learned something from me, but I certainly learned a lot working with them. And that's it. Thank you very much. Okay.
That you put my picture close to me.
Okay, but I can't tell you why, but no. Picture touching, no, you cannot talk about age. We are referring to. Thank you. It's late.
No, people are impressed. That would be great.
I have a question.
Collaborate better between scientists and engineers in this field.
Yeah, it
Because it can open really the new frontiers for different applications.
you know, the real, and this is real, it's not just to give a fancy motivation. Why I started working on tactile sensing was because I was keep on writing at the beginning of my papers
Let us suppose we have a force sensor. Let us suppose we have a tactile sensor. And then I started writing equations. And at some point I said, okay, let's have a sensor. And so I stopped writing things which were not possible to demonstrate. And in a cycle of development, we arrived to size cubing. And so the real problem is that it's not easy to create a community of people working from the, let's say, high level. When I say high, not because it's important, because when you integrate things, you are collecting stuff, and you usually collect components which have not been designed specifically for what you need. And this is always leading to suboptimal design. So when I was talking about the national doctorate, the idea would be to create people oriented to work on robotic problems, starting from the fundamentals, and certainly fundamental technology, science, as you do in materials and so on, is a critical topic. There is still, I think, a problem of time scale, because integrating a robot could take weeks. Developing a component out of a new principle can take years. So if there is something that should be somewhat done, it's to create a pipeline of work, so that new ideas are going to be developed, but there is the push to transfer them to components and then to system. We are working in a spot way. Sometimes there is some innovative or disruptive technology which maybe it's picked up. For a long time we used I'm talking about very, very low level things. For a long time, we used for the networking of the sensors using canvas. Canvas is, it has not been made for robots. It's nice, but it was made for cars. And it was designed in 1985 or so. So it's a 40 years old technology. And we used that until really, literally, yesterday. So, and why? Because it is cheap, it is very simple, but it's definitely not fit for what we have to do. So I think it could be the time of using and developing technologies which are not made for cars, but made for the machines which are used to make cars. Which is another way of looking looking at the proof.
Yeah, I have a question. I mean, like you discussed the aspect of the fact that there is an interest of having humanoid, because of course people are seeing the potential of the market of having cobot or anyway robots in our houses and doing for us our chores. However, we have for example, as you said, Jeff Bezos investing in Microsoft, and we had some example, for example, of Elon Musk that were showing a humanoid made in 6 months, or very short time. However, what I noticed is that the majority of them are looking at tactile sensing mainly in the aspect of manipulation with hands, but they are overlooking completely the whole aspect of the interaction with the body and so the safety. why you think, I mean, they have definitely resources, economically speaking, about all, so to be able to potentially integrate also skins on the body and so providing more safety. What do you think is the reason why they're not like seeing that, or like, or do you think there are some challenges as barrier towards like having like this sensing humanoid?
Yep. One good question before was, which is the cost of the skin? Now the cost of the skin could be twice the cost of the robot, except for other particular aspects. So the skin is the largest organ in humans. It's 2 square meters more or less. And you have a huge number of sensing elements. They are not uniformly distributed, but they are very little. Of course, if I want to sell a robot, a fully sensorized robot, the cost of the skin should decrease. There was one idea at the time when he introduced this, which was the idea of developing self-healing components. Why self-healing? Because the skin can be easily cut, can be easily damaged. As a matter of fact, one study that we made with Alessandro was to test the robustness, not just the robustness against the failure, but the robustness of the computational models to keep on recognizing the contact when the tactile elements could fail. And we got impressive results because the resolution of the components we are using, it's definitely much higher than what is nominally requested to recognize the touch of the hand. I would say that, except for a few failures, this skin has never broken. So you can break it when you install it on the robot. It can happen because of the reasons the custom is definitely a poor solution. We enter in the same discussion I was making before. We are using the wrong technology to do the good thing. But this might be a topic for investigating alternative solutions. And optical transduction might be one. You do not have anything to break. You cannot break the air. So in this sense, a better engineering, and I'm responding to your question, maybe a better engineering, a better capability, an improved capability to design customized components, which is totally out of our capabilities, could go into the direction of building the right component for the right application, for the right robot, with a given specification. You know, because you need which is the value of simulation in that. So it's part of the engineering of this kind of components. So, certainly, one goal, and I personally stayed away from that, is the miniaturization, the real miniaturization of this technology for sensorizing the fingertips. We have done few examples, few experiments with quite large fingertips. I mean, Shrek-sized fingers, and okay, it works, but reducing by a factor of 5 times the dimension of these components, it's not an easy game. And again, the micro technologies might be in support. So it's just a matter to focus the research at basic level toward the final application. I don't know if it's doable. engineers live with the screwdrivers. In their hand, you live with working with tiny electrodes and microscopic stuff. I think that, that those are screwdrivers at nanoscale level. So the point is whether it is possible to think of that level, the work at the level transposed to a final application. I think it could be possible, and maybe the $2 million might serve that. I don't know. Maybe.
You're looking at giving robots skin, basically. Would it be an idea to give robots instead clothes that are clothes, sensitive clothes, basically?
Yeah.
I'm asking this because we've developed in another project a pressure shock, which basically measures touch not on the outside but on the inside to measure pressure from a foot. But this could be one way, perhaps, also to miniaturize things and make things more flexible by having it in textile. So this is integrated in textile, where perhaps it would be more flexible than having a skin that is basically, once it's on the robot, it stays there, right?
Yeah, definitely. I mean, it's another way. It's another way for seeing similar problems.
Yeah.
There is, I think I can say, Tella is working on technologies for implementing sensors, tactile sensors on the high strain parts. The elbow, the knees, where you have a very high strain, you're bending, and this is a challenge. But it would be a challenge also for garments. Astronauts, spacesuits are a good example of this type of application of this type of technologies to gain spatial awareness. And a spacesuit is like a balloon filled with air, so it's quite rigid, and it's not easy to move, and it's definitely almost impossible to get a feeling of the contact that you have with the surrounding space. There have been studies by people at NASA to at least to sensorize the fingertip and to reflect to the fingertip of the astronaut inside the feeling of the contact. They are simple, making things that could work in space is horribly hard for many reasons. And so, yeah, there is room to go in that direction. And I would say not just for robots, but this might be one example. And there are certainly other where having or gaining a spatial awareness for a human worker might be important.
Yeah, it's
surgical robots. This is another example. Now, surgical robots provide or should provide tactile feedback. There has been a lot of work in developing tiny miniaturized force probes to measure the mechanical impedance of tissue to recognize tumors or other types of disease. And this information should be reflected back to the surgeon, which is operating maybe 3 kilometers.
Yeah, another application would be people who have lost sense of feeling, hands or feet or body.
This is okay. This is another order of complexity, because in that case, in the case of amputees, just there was a.
If it's entirely missing, okay, but.
Yeah, no, I'm referring to this because it's an extreme case.
Yeah.
I think the guy, it was Silvestro Micera from La Scuola Superiore Sant'Anna. Couple of years ago, 3 years ago, he made, it was an amazing experiment to use tactile feedback from a prosthesis to a person, an amputee, by implanting electrodes on the terminal nerves. And it worked. So, I mean, putting something across the skin, it's not an easy job, but technically it's doable. And we're entering exactly the same line of reasoning as before. So you need a technology which fits your end. Okay. So this is.
That's
Yeah.
plenty of work.
Thank you very much.
Thank you very much for really nice talk. This is the end of our meeting of this wonderful seminar section. I thank all the speakers and I thank very much participants in person, also those online. Thank you very much and have a good afternoon.